All right, so I'm going to share a screen with you that's basically what's going to be on the test
Okay.
for this one. So you see this Word document, right?
Yes.
All right, so this is things on the test. And so they're going to be four derivative problems, the initial value, four integral problems, related rates, the epsilon delta proof. There will be a problem about continuity, for limit problems, a definite integral with indefinite limits, and then the definition of derivative things. So looking at this, is there something that you would want to start on that you find harder than others, or should we just work through it from the top?
Just kind of go through it.
All right. So, I guess in ways of the derivative problems, I will go back to. I'll stop sharing here for a second. So, in ways of derivative problems, like we really haven't added really any new rules, I don't think, in this past couple weeks. And so, as I was looking through the test, there are some things that I thought would be helpful when computing derivatives. And the first one was, I guess, to recover the change of base formula with logs. So I don't know, but so if we have something like a logarithm of base like 7 of, let's say we have something like this, and we want to take the derivative of a function with this log. And to really do this, we have to use the change of base formula, which basically we can change what base this is by, and it's kind of easy because we can change it to base e, because log base e is equal to ln. And so we are going to change this to be the log says you can say that the log of base over the log of I guess. So we can change this to actually be this ln of the argument over the ln of our base. That's basically what the change of base formula says. And now we know how to do this derivative, whereas before we didn't. So this is kind of an algebra problem more than a derivative problem, because this is very hard. Because we can take this one, the 7th out, because this is a constant. And then we can solve this derivative by using the ln rules, which would be 1 over u, so this 4x squared plus 3, times u prime, or 8x. So then our derivative would be, it would be 8x over 4x squared plus 3 times the ln of 7. That makes sense what we did there?
Yeah.
So that was one of the things that it was hard for me to remember that you had to do this. Other than that, the derivative problems on the test, I think, are kind of straightforward. They're not like super hard. There's lots of chain rules going on, but I guess one other thing to cover is derivatives where you have to use like the ln of something to get it out. So if we had like y is equal to like x to the x squared plus 3 or something like that. This is kind of hard to see, but so we can use the ln's again. So if we just take the ln of both sides, we can use log properties to drop this power in front. So we can say this ln y times this ln x. And then we have to use implicit differentiation. So we kind of did this last review, but I felt like it would be candy to cover again. So if we take the derivative of this, 1 over y, and then we get this dy dx out because we kind of have to chain rule it. And then for this one, we're going to have to use product rule, right? Because we have two separate parts. So it's the derivative of the first, which would be 2x times ln x, plus the derivative of the second times the first, which would be x squared plus 3 over x. And then we simply just multiply the y over to get our dy dx by itself, 2x ln x plus, and we will change this y back into our original function because we know what y is, and that would be our derivative. So this is also kind of useful to remember for this test. The Allen tricks are kind of useful. So other than that, for the derivatives, I would cover really well the rules for in inverse trig functions. I would brush up on those, especially stuff with like let's say we have, let's just do like tangent inverse of like 8x, right? If we're taking the derivative of this, we got to remember that one. Let me find my notes. So the inverse. So the rule says that we can have like that the tangent inverse of x is going to be 1 over 1 plus x squared, right? Well, we got to remember that this is kind of a u function. So if we change this to a u, we're going to have this u squared down here. So if we took the derivative of this, we're going to have times kind of by this u prime out here, right? So we know that this is our u, so we're going to have this u squared on the bottom. So we're going to have 1 over 1 plus our u squared, which is our u is 8x squared. And then we're going to multiply it by the chain function, or the derivative of the inside function, which is 8. So then our answer would be 1 over 1 plus 8x squared, or 8 on top. So just brushing up with stuff on the inside and remembering chain rules will help a lot on the derivatives. Is this too far over? Can you still see this?
I can see it.
All right. And so that kind of covers it for the derivative problems. I guess so. Next would be our, integral problems. We'll cover those real quick. So one thing that would be kind of handy is to recover, the completing the squares. So I can have a problem just to cover real quick. So if we had, let's say, the integral of 1 over x squared plus 14x plus 65. If we look at this, it's kind of hard to see what to do with this one, because we can't do a u sub here, and it's not an ln function really. So the way we complete this one is by completing the square. And so we know that squares are going to be like that. This is the formula for a square function. So if we have a square, this is what it's going to look like. So we're going to take this and rewrite this as x squared plus 14x. We're going to leave kind of this blank space here is equal to negative 65. Well, we know that these two terms are going to be the same. So here we can basically say 14x is equal to 2ax. We can say that a is equal to 7, right? And so the square is going to look like this x plus a squared, right? So this is going to be a 7 squared because we found what that is. So if we add a 7 squared here, we got to add it to both sides, right? And then, so then we're going to factor this into to our square. So we're going to have x plus 7 squared, and this is going to be equal to 65, 49. It's going to be negative 16. And then we can add this over to get our x plus 7 squared plus 16 equals 0. So now that we have this in a better form, we can replug it into our integral up here. So we have the integral of 1 over x plus 7 squared plus 16. And this, we'll rewrite the 16 actually to be a 4 squared. And this is inverse tangent. And we're going to, it's 1. So the inverse tangent rule is 1 over a. So if we have this, we have, I think it's x over a. So if we have the inverse tangent of x over a, it's going to look like 1 over a. Actually, I think I wrote that wrong, but I'm bad with rules. I can remember what to do with them, but essentially it's going to be 1 over 4 inverse tangent of x plus 7 over 4 plus c. And that, so if we have, yeah. So does it make sense?
Yeah.
All right. So I guess that's one thing to remember, is just completing the square is helpful on some of the problems. A lot of this test, and I don't feel like there's a whole lot of new calculus concepts. There's a lot of algebra stuff going on. And I guess other than that, on the integral problems, I guess there's one other thing to cover. So if we have an integral like this over these can be kind of confusing because at first it looks like it's going to be a U substitution problem, right? Because we have a difference of power by 1, so we can say, well, it's a U sub. But if we work it through that way and we say that this U is equal to 1 minus x squared du is equal to negative 2x dx, really the x's aren't going to cancel out because we have this as whole one term. So as it's written right now, this is not going to be a U substitution problem. So I feel like that can be kind of tricky. I think this is +8. I don't know. I may have changed it. But to solve this problem, we're basically just going to separate this into 2 parts. We're going to use some more algebra stuff. We're going to say 4x over, and then we're going to have plus the integral of 8 over the same thing. So really, we just split the numerator and then split our integral, and then this problem does become a U substitution problem, right? So we can say that our U is equal to 1 minus x squared. Du is negative 2x dx. Then we can replace this dx for, so we have 4x over u times du over negative 2x. And these x's will cancel out, or we can take this negative 4 halves, or negative 2 out of our equation. So we can have -2 times 1 over the square root of u du. And then this is u to -1/2. And we'll raise it to power u to 1/2, and we'll divide by it 1/2, or multiply by 2, so 2u. And then we can't forget that it's got a -2 out front. And so that's for this side of the equation, and we're gonna have a plus. Is it too far down?
Yeah, I can only see u to the -1/2. That's the last thing I can see.
What? Can you see it now?
Yeah.
All right. So now we kind of have to go back up and solve the other side of our equation. And so we can pull the a out and have 1 over 1 minus x squared, right? And then this becomes an inverse tangent problem, right? Because we know the derivative of inverse tangent is this. So we can say that that's just going to be 8 inverse, not inverse tangent, inverse sine of x, right? So then we just make sure we resub our u back in. And so we have -4 times 1 minus x squared plus our 8 inverse sine of x, and our plus c at the end. So out of ways of integrals, I would definitely brush up on inverse trig functions and the rules associated with those. And I guess the algebraic tricks of completing the square and just like splitting stuff up like this. So those are very helpful. I guess, well, while we're on the topic of integrals, I guess we'll cover the definite integrals with indefinite limits. So let's say we have an integral of 1 over x dx, and we want to solve this integral from 1 to infinity, right? So we can't really just plug infinity here, right? It doesn't. So we have to. We're gonna do the limit thing. So we're gonna pull this out. We're gonna say, let's take the limit of the integral. We're gonna replace this with a variable. Let's say a, as a approaches infinity, of 1 to a of 1 over x dx. And then we're just going to solve the integral, which we know this is ln of x. And we're going to evaluate that from 1 to a, right? And so we're going to have ln of a minus the ln of 1. And now we can say the limit as a approaches infinity of this whole function. And as ln approaches, as a approaches infinity, this also goes to infinity, right? The higher number you plug in to an ln, the higher number you plug, you'll get out. So this just continues forever, and the ln of 1 is 0. So our answer in this case is going to be infinity. So, and if you look at it, it's kind of like, oh, the function. Well, if we have a graph per se of ln, which looks something like this, as if we want the curve as x goes to infinity, right? It's going to be infinite. So if we're taking the whole bounds, it's going to be infinite, right? But that's not always the case. It's kind of a weird concept. Sometimes infinity has an end. So if we take the same problem, we have this infinity of 1 over, let's say it's x squared dx, right? So we're going to do the same thing. We're going to pull a limit as a approaches infinity. We're going to put some bounds like this. And so now we solve that. So that's x to -2. We solve the integral. That would be x to -1 over -1. So that's equal to -1 over x evaluated from 1 to a. The limit of this problem as a approaches infinity. So we're going to have 1 over a negative 1 over a, minus a negative 1 over 1, right? Well, and this is going to be the limit. And if we think about this, if we have a number and the bottom approaches infinity, this is essentially going to go to 0. If we take a number and divide it by an infinitely large number, it goes to 0. And then we have this negative minus a negative 1, so that becomes 1. And so really, the answer to this problem ends up being 1, which is kind of an interesting thing when we think about where we're taking an infinite limit, and we get out a definite answer. So that was one thing that I thought would be helpful to review and prep for this test. Do you have any questions on this?
Nope.
All right. All right. So I guess next would be a related rates problem. So kind of just reusing the same old problems because this is what it would be helpful for the test. So let's start with the cone again. You could probably go rewatch last week's or last review and get similar things. So the area or the volume of a cone is equal to man, I can't ever remember this one. You won't have to remember, it's on the test. All right, it's pi r squared h over 3. And let's say that we're pouring sand into a cone or something like that, and we're pouring at a rate of 1 cubic feet per minute. So, or let's say not 1, because that becomes easy. So let's say it's 3. And let's say that this cone is 8 feet tall and it's 6 feet across. And then let's say how fast is the height changing when h is equal to 3 feet. Or when we're 3 feet up the cone, how fast is the height changing? And so once again, we have to recognize that both our r and h's are dependent upon time, because as time goes, our radius will get bigger as well as our height, right? And that's kind of an important concept to remember. So we have to come up with our ratio. So if we take just kind of a side section out of this, and we have this r and we have this h, we have the height is 3. That the radius so r over h is going to equal this 3, and the radius when h is 3. Sorry, I'm drawing a blank. Oh, man, why can't I think through this anymore? And this happens when you don't have a whole lot of time to prepare for this stuff. Yeah. I forget something about the problem. I don't know. Why can't I think of this? And you got any ideas? I guess we'll just call this R, right? So this ratio is going to be the same, so that's just going to give us our height again, right? And this is pretty bad. I'm sorry. I wish I was a little more prepared. All right, yeah. So that. All right, now I know what I did wrong. Okay. So we're just going to use 8 and 6. There we go. I got it. So I was drawing a blank. So essentially, we're going to use this triangle to find out the ratio of this triangle. We're going to use the whole big thing. And this would actually be the radius, which is 3. So 3 over 8 would equal R over H. And now we can find the relationship between R and H. So we have 3H is equal to 8R. And we can say that R is equal to 3 over 8H. So that makes sense. Sorry, I just drawn a blank there. So we're basically going to plug back this R into this equation so we can get rid of this R variable and all be in H's. So our volume is going to be pi times 3 over 8 H squared times H over 3. So that would be 9 over 64 H cubed. 64 times 3. 192, I think. Right. We can just get a factor out of 3. That works. All right. So now we can take the derivative of this. We can take all this beginning function stuff out and just take it times 3. So we're going to have this volume times pi times 3 times 3 times h squared dh dt over 64. And now we can plug in all our numbers that we have. So, or this would be dv dt because we took the derivative of it. All right, so we're going to have 3 is equal to this pi times 3 over 64 times 3 squared. It's a lot of 3's, dh. And we can plug this into our calculator to find our answer. All right, I forgot to put my dt down here. And I found the dh dt to be roughly 0.75. And this would be feet in a minute. So this, I guess, like concepts to cover and to remember is this is kind of important to remember that these R and H's are also dependent on time. I don't know if you've done the cone problem probably lots now, but it's probably the one that will help you most on this test's related rates problem. So I guess, do you have any other questions on this?
No, I don't think so.
All right. So I guess next would be the epsilon delta proof. So what an epsilon delta proof is doing is it's essentially proving a limit. So we know, so if we think about what a limit is, a limit doesn't really care about what the actual thing is. It kind of cares about how we approach it. So if we wanted, let's say we have the limit as x approaches 3 of 2x minus 1. We know that this is going to equal 5, right? We can just plug it in, and 6 minus 1 is 5, right? But we want to prove that this limit exists and that it does equal this 5. And so that's what the goal of an epsilon delta proof is to do. It's to prove that this is true, that this is a true statement. And to really like understand it, we start with a graph. We will graph our function, right? So 2x minus 1. So we start at minus 1. We go up 2 and over 1, and up 2 and over 1. And we need to be at 3. And we'll go one more, 4. So we'll have a line that looks something like this. Sorry, not the best to scale drawing. But epsilon it itself is kind of a small change in the y direction. And delta is a small change in the x direction. And so saying at this limit at x equals 3, right, there's going to be some bounds, right? So these would be epsilon bounds. And these would be delta bounds. So this would be like minus delta, and this would be plus delta. And so there would be some delta function or some x value that you would plug in that would give you a value really close to our actual limit. Does it make sense what I'm saying there? So a limit doesn't care about what the actual function is. It cares about what around it is happening. So this is going to basically what we're going to do is we're going to say that if we take this point, it's going to give us a point really close to our limit or 5. And if we take this point in between here, we're going to go delta to the right or delta to the left. That is going to be epsilon to the right and epsilon up or epsilon down of our actual function. So it basically says we're going to be really close. And that's going to prove our limit because we're going to say that, oh, we're really close. If we move a little bit to the left of 3, we're still real close to 5. If we move a little bit to the right of 3, we're still going to be close to 5. And they just write that in a very elegant way, probably more elegant than I can. And they use a bunch of notation for this, and I think they probably want you to use the notation on the test. But it's basically saying that for every epsilon greater than 0, there exists delta greater than 0, such that our function minus the limit of less than epsilon when our I missed something. X minus our limit is equal to delta. And so this is kind of a complicated way of saying what I was trying to say, that for every epsilon around where we're going to have a delta that corresponds with it. Or for every delta, there's going to be an epsilon, back and forth. And they use a bunch of funky notation for this. I don't know if you've covered it, but it's kind of strange. So for every, they write as an upside down A, epsilon greater than 0. There exists is a backwards capital E. Delta greater than 0. And such that is kind of this backwards, not quite so capital E. And so then it's just basically the same, such that epsilon when and sometimes you'll see when as kind of this double arrow, this equal sign with like an arrow on it. But this is probably, both ways will probably be acceptable if you write it out word for word or if you write it in notation. Notation looks really funny. It looks like an alien language. But essentially now we're going to kind of go through our algebra steps that kind of show that this happens. So we're going to take our two parts that we have, our function, which is 2x minus 1, minus our limit, which is 5, right? So we have this function, 2x minus 1, minus our limit, minus 5. And that's less than epsilon, right? And then that's when, and it's this statement, this x, and a is this what our kind of our x value, what x approaches. So we have minus 3 is less than delta. So we can simplify this down to say 2x minus 6. And then we can simplify that even more by pulling a 3 out, right? X, or 2 out, sorry, my bad. Minus 3, right? And it's going to be the same statement here, right? And it's basically the same statement over and over and over again. But now we can see that we can divide this 2 over, right? So we have this x minus 3 epsilon over 2. All right, and now we can kind of see that if you look here, they're essentially the same thing, right? This delta. So we can now replace this with our delta. So we can say that delta, as that, you can still see that, right?
Yeah.
So that's basically our relationship. So we were talking about how if we go a little bit delta to the right, we're going to be within epsilon up here. And so this is kind of like that relationship that describes how those behave. But now we're going to kind of like finish our statement. So this is our kind of our opening statement that says we're going to prove this. And this is kind of our math that shows that they're related. And now we're going to say like, so let our delta equal, that's a 3, not epsilon. Epsilon over 2. So for, yeah. So then every x in the delta interval will produce a y value, or I guess interval around 3, right? Because that's where our limit is. Because this is x equals 3. So for every x in the delta interval around 3, it will produce a y value in the epsilon epsilon interval around 5. And so therefore, the limit as x approaches 3 of 2x minus 1 is equal to 5. So it's kind of a weird, it's a very formal statement of how to say it, but essentially it's just saying that if we go a little bit to the right, we're going to be really close to 5. If we go a little bit to the left, we're going to be really close to 5. And that proves that the limit at that point is going to be 5. Does that make sense?
Yeah.
All right, sorry, it's kind of weird. You probably don't have to 100% understand it right now. Sometimes I'm not very great at explaining it because I don't feel like I've understood it for very long. So essentially, you just need to know that they're looking for this kind of stuff. So this closing statement and this opening statement pretty much have to be verbatim. That's what they're expecting. And this middle stuff will change based on the problem, but it should look something like this, where you have your statement, and then it says when they're equal to. Because we were working with both that delta and epsilon, so you can't forget either. So, so I hope that this is helpful in this one. This one I think is kind of an abstract problem. All right, so are you good on this? You good if we erase this?
Yeah, you're good.
All right. All right, so I guess next would be a continuity problem. So I don't think these are very hard, so I don't think we'll spend very long on it. But I think it's just to remember if a function is continuous. Function is continuous if the limit of the function as x approaches a is equal to the function at a, then this constitutes a continuous function. So if this isn't true, then it doesn't work. And so if we say, let's say like 2x plus 3 is equal to our f of x, right? Well, this, we already know it's a continuous function, right? Because it's just a line. There's no like breaks in it, right? But if we wanted to test it, we could say, well, let's say our limit is 3. So when the limit of x approaches 3 of our function, or this 2x plus 3, then that's going to come out to be our 9, right? And if we just plug in 3 to our equation, we also get 9, right? So if we put and so like this comes in handy when we have like a piecewise function per se. So if we have two functions, so let's say that it's 2x plus 3 for any value greater than 4, right? But then it's like minus 3x plus 7 for any value less than or equal to 4. And so then this becomes more of a problem where we have to check the limit as it's coming from the left side and the limit as it's coming from the right side. And then we have to try the point. So the point in question here, because we know that this would be continuous, the whole function, this would be continuous. The question is this just continuous at the point 4? And if you really wanted to, you could graph it, and that would really help you, because if you remember, if we have a break and a graph, right? It's not continuous, even if. All right, so I don't think there's a whole lot of stuff to do there, but just remember this about continuous functions. This, if the limit of the function as it approaches value is equal to the function at that value, then it's continuous. Any questions on this? All right.
I guess I'm just a little confused because you had like, see the limit as x approaches 3 of 2x plus 3 equals 9. And because you had, I understand like plugging it in, you get the 9, but then you were like, it equals 9.
So this one, the limit as it approaches 3. So like if we graph it real quick, right? So we have 1, 2, 3, and that's high up there. So this would be our point. Because if we plug in 3 for this point, right? So if we plug in 2, we'll get 7, right?
Mm-hmm.
7, all right. And if we plug in 3, we'll get 9, right?
Yeah.
And so we have a line that looks kind of like this. So if we think about it, so a function, like, it's continuous. There are no breaks or anything, right? So the limit as x approaches 3, so limit kind of works with how it's coming from both sides, right? So for limits at 3, if we approach 3 from the left side, it basically approaches really nice, right? It's basically a straight line. If we approach it from the right side and we're coming down the line, it also works, right? It also goes towards 3. And so if that's the case, then the limit exists, right? And it's saying, so if there's a limit that exists and the function itself at 3 is equal, then it's continuous. So it's kind of a way to tell if a function is continuous or not without having to graph it like we did here. Because sometimes problems would be pretty annoying to graph, right? So if we can say, oh, if we take the limit of a function and we plug that value into the same function and we get the same thing out, then it's continuous. Does that make a little more sense? Are you still? I don't know if I explained that super well.
So it's basically just saying like, so you have the limit and you're plugging like the limit in, and then you plug, I guess technically that same value into the function.
Yeah. So this character.
So it's just.
All right. Keep going. Sorry, I interrupted.
I mean, I guess it makes sense. I don't know.
It
makes sense. I'm still confused at the same time.
It's really simple, and sometimes I think it might be a little easy to overthink it because the limit as x approaches 3 of this particular one is 9, right?
Mm-hmm.
So, but the value itself, right? So 2x plus 3 is equal to f of x, right? So that's our function. Yeah. So if we plug 3 into here, we also get 9, right? And that's what it's saying, that if we have a limit, and the limit at this point, or the limit as it approaches 3, or the limit as it approaches a, or whatever this is equal to that function with that same point plugged in, and those two are equal, then it's continuous.
Okay, that makes sense.
All right. Yeah. So, like, really, they really aren't, like, super complicated problems. They're pretty simple. I mean, all you have to do is you just have to find the limit and plug it into the problem, and if it's the same, then it exists and it's continuous. And the problem on the test isn't much harder than this. Maybe I shouldn't say that, but the continuity problem is very hard. I guess we kind of talked a little bit about limits. So there are some limit problems on the test. And I guess just remembering the L'Hopital's rule is kind of handy. I looked over them, and I wouldn't say any of them are crazy. I guess maybe brush up on Koch and Cinch and stuff. But we're kind of running short on time, but I think that actually covered pretty much everything. So I guess, are there any other questions about stuff that you want to talk about before you take the test?
Not that I can think of.
All
I think
right.
you've covered them well enough, and I feel better about it.
Yeah, I hope that this helped a little bit. Sorry, I
Yeah,
blanked in the middle there, but yeah. Problem I've done 100 times, and whoops, can't think. Sorry, but